All right, this is chapter 7, section 3, using the central limit theorem. So now we're going to do some of just applied problems. So essentially, no matter what the distribution is, you can use the normal distribution, or the bell curve, to estimate the problem. Even if it's not normal to begin with, this is what we proved in the first section, right? So let's say that the data is uniform, which is what we did with the quiz one with the little kids, right? They had 4 quizzes, and we proved that we could make the normal one, or the uniform one, into a standard one, right? So let's say the data is approximately uniform, min-max values of A and B, correct? We could actually make it normal, do estimations. So let's say we have a study conducted among students at a college campus to determine stress. The stress scores are between 1 and 5, right? So you can choose 1, 2, 3, 4, or 5, and if you graph the data, it's going to be uniform, basically. 1, 2, 3, 4, and 5, right? So the same number of people pick each one, essentially, right? Okay, so we need to calculate the mean and the standard deviation for a distribution, no matter whether it's normal or not. And the formulas for mean and standard deviation are going to be different for each type of distribution. We're not going to do every single type of distribution there are, because that's not possible. But if we do uniform, these are the formulas, right? So if we do uniform, right, this will be 1 plus 5 divided by 2, right? So that's 6 divided by 2. So that's a 3 is my mean, right? And my standard deviation would be 5 minus 1 squared divided by 12, right? Square rooted. That's right, that's 16 over 12. Square rooted, right? So that would be my mean and my standard deviation for this particular distribution. So I have to use these formulas if they're in fact a uniform distribution. And one thing I will say is you can go through the process of doing basic arithmetic to simplify the radical all the way down. You can normalize the denominator if you want and get this. That is not necessary. If you want to use the unsimplified version or a slightly simplified version, that is fine. My recommendation is to use one of these two so that you don't have to use extra sets of parentheses when you type it in the computer. And don't do a decimal value. This is approximately some ridiculous decimal value that goes on forever. Don't estimate. Use the exact value. Use one of these two. Don't use this one because you'll have to use extra set of parentheses, and that's going to be annoying. And propensity for mistake is high. Okay? All right, so let's say we have 75 students that take this test. What is the chance that the average of the group is 2 or less? So a very small probability, 2 or less, essentially, correct? Okay, so let's try this out. So this will be normal dot distribution. So 2 or less is what we have here, correct? 3 was the average, and the standard deviation was the square root of 4 divided by 3 when I simplified it, and then divided by the square root of 75, which is the sample size. Okay, so that's going to give me about, okay, let's go out here. Okay, and just make sure it's set on number, and then just make sure you go the correct number of place values so you can actually get an answer, essentially. All right, so here's the problem. This stress score thing here, the average is 3, right? That's what it said. But the problem is this goes to negative infinity, but this can only be 1, 2, 3, 4, and 5. So this actually does stop at 1. So we actually want this area. The question is, this little piece of area out here that goes to infinity past 1, is that going to make any difference? Well, let's check. So if I take this, copy it, and do minus, paste, and put a 1 in there, is it going to make any difference? So 2 or less is only 2 and 1, essentially. It doesn't appear to make any difference. Okay, it does at some point with the decimal places. It will make a difference, right? But in this case, it's not going to. The two decimals are too small, essentially. So whether you account for it or not, it's not going to make a difference in this particular case, right? So whether you account for it or not, this isn't going to make a difference for you. Okay. Okay. Let's say we want the percentile, a 90th percentile. So if I take 75 students and take their average, okay, what would the average of that group be? So obviously the average is 3 in this particular thing. So 90th percentile should be more than 3, essentially, right? Okay. So normal dot inverse 90th percentile, comma, 3 is the average, and then the square root of 4 divided by 3 divided by the square root of 75. Oh, add an extra 0 there. There we go. All right, so that's about that number of points essentially, right? Okay, so if I take 75 students and I average them up, what do I get? Notice when I do this, I'm putting the square root symbol here for you, but in the actual spreadsheet, I have to use the word command to get the square root. Okay, so the next one says the total. Okay, so I take 75 students and I add them up. So it's not the it's not the mean of the sample now, it's the total, right? So this says 225, you're like, where the hell does 225 come from? Well, the mean is 3, isn't it, right? The mean's 3 times 75 students, that is 75, right? So we want less than 200, so that's less than 200 over here, correct? Okay, let's see what that is. So we go to my spreadsheet, that's normal.distribution, 200 or less is the sum, and then we have 3 times 75, and then the square root of 4 divided by 3 times the square root of 75, comma true. You're like, well, this makes sense, right? There's 75 of them. There's a 3 average, right? So that's 225, right? That's the mean of the sum. I want 200 or less. Okay. The standard deviation is this, but why are we multiplying by that and not 75? That's the question. Well, if I have the square root of 4 over 3, the standard error would be divided by the square root of 75, correct? So if I times it by 75, this whole thing is the same as this. Well, you're like, why is that? This is the shorthand way of doing it. Why? Well, if you remember what square roots represent in pre-algebra, square root is the half power, isn't it? And this is the first power, right? Because again, there's 75 students, so we're timesing it by 75 to get the sum, correct? Well, 1/2 and 1, so if I cancel, this is going to leave me with a 1/2 here, isn't it? Because 1/2 divided 1 minus 1/2 is a half, which essentially is this shorthand here. Essentially, so that's the easier way of doing it. If you want to put all of this in, you know what I'm saying, with the square root of this on the bottom and then times the 75, you can do that. It's just a lot of parentheses and propensity for mistakes. I would not recommend doing that. Okay, so it's about 6% chance. Not a very good chance, essentially. But you're like, wait a minute. The lowest I can get is 200, right? No, lowest I can get is 75. So I'm going to copy this and minus this, and I'm going to do 1 times 75. Right? And you're like, why did I do that? Well, if we look at this, the question is, the average is 300, right? No, 225. I'm sorry, 225. Average is 225, right? Which is 3 times 75. And we want to know 200 or less. The problem is this goes to negative infinity, which is not possible. So 1 times 75 is actually the lowest value, correct? So if we don't account for this over here, does it change my answer, right? So we want 200 or less. The lowest I can get is 75 people selecting 1, which would be nearly impossible. Okay, so if I don't account for that, I would not use this, but I am using that. Okay, so if I hit enter, I get this amount here, 0062. Does it make a difference whether I get rid of this or not? No, it doesn't. Not to the number of decimal places we care about, because essentially, what's the chance 75 people are going to select 1? Almost none. So that little piece on the end of the curve is not going to account for all that much, as long as we stay within, 4 or 5 decimal places. You know what I'm saying? We're more than fine. So whenever you do these, never give like 1 or 2 decimal places. Give at least 4 or 5 decimal places in all these answers. Okay, next one. Let's talk about the symbolism here. So notice I'm saying the sum of x, right? So the sum of the individuals is less than 200. Versus up here, I'm saying the probability of the mean is less than 2, right? So it's the sample mean of 75 is less than 2. So there's the difference, right? The sample mean versus the sum of the individuals. Okay, determine the 90th percentile for the total sum stress scores of 75 students. Okay. So normal dot inverse, 90th percentile, okay, 3 times 75, comma, the square root of 4 divided by 3 times the square root of 75. Because again, it's not saying the sample mean, it's saying the total, right? Go back to the question. It says the total, so I'm adding up all 75, correct? So if I add up 75 students, 3 at 75 is 225. That's the average. So 90th percentile is above average. So this should be more than 225 if I add up 75 students and we're in the 90th percentile of samples. So if I do that, what did I do wrong here? Should be number. Did something wrong. Oh, 0 point. That's why. Obviously, you can't do 9 millionth percentile, whatever it was. There we go. 237 points, essentially. Okay. All right. So, there we go. It's a 90th percentile. Probably should label that on the front, but that's okay. All right. So what this is saying here is, what's the probability the sum of the individuals is more than 170? So this is 170 here, right? So what's the chance it's more than 170 for the sum of them, right? Notice there's no x bar above it, right? There's no x bar. Not talking about the sample, we're talking about the individuals. So you probably could put xi there, to be honest with you. Okay, so normal dot distribution, right? 170, comma, 3 times 75, comma, square root of 4 divided by 3, times the square root of 75, comma, true. Okay, the problem is this is 170 or less. That's not what I want. I want 1 minus which would be more than 170, correct? So again, make sure it's on number and add a whole bunch of different decimal places there so you can get out to a reasonable, because it's not 999 forever, essentially. Because if you had not enough decimal places, you might think it's 1 or 999 forever, but it's not. Okay? So, what this is saying is the sum of the group, right, being more than 170 is probably pretty close to 1, essentially. Okay, that's the end of the first video.